So, moving on to the next part of our discussion on wave motion, let's take a look at a few examples. We have examples part 1. First, we have sample problem number 1. You have a wave traveling along a string. So, it's wave on a string. It is described by the following wave function. Y of xt is equal to 0.00327 meters. Sine of bx minus ct, where b is equal to 72.1 radians per meter and c is equal to 2.72 radians per second. Determine the amplitude, wavelength, frequency, and speed of the wave, as well as the wave's direction of propagation. Now, wave traveling along a string, wave on a string, periodic wave by default. We use sine function, and indeed, if you look at the wave function given, sine function is used, further telling us that we have a sine wave. The equation, the general equation for a sine wave is given by y of xt is equal to ym sine of kx minus plus omega t plus phi. Comparing the general equation for a sine wave with the equation provided by the problem, we see that bx minus ct, there's no plus phi or plus additional angle, which tells us that the phase constant phi is just equal to 0. Kx, bx, omega t, ct, plus phi, no additional angle, so phi rather is equal to 0. And minus plus, minus, so kx minus omega t, which tells us that the direction of the wave is towards positive x direction. Ym is the one multiplied to sine function. Ym is the amplitude. In the given equation, the one multiplied to the sine function is 0.00327 meters, which means this is the amplitude of the wave. Ym is equal to 0.00327 meters. Comparing the two equations further, you have kx, bx, which means k is just equal to b, and k is the wave number is equal to 2 pi over lambda, which means b is equal to 2 pi over lambda. Isolating the wavelength, lambda is equal to 2 pi over b. 2 pi divided by b, we know b, given by the problem, 72.1 radians per meter. Thus, we are able to calculate lambda, 0.08714542728 meters. Likewise, you have omega times t, omega t. In the given equation, you have ct, which means omega is just equal to c. And omega, angular frequency, we know one equation of omega to be 2 pi frequency, which means c is equal to 2 pi frequency. Isolating frequency, f is equal to omega over 2 pi. And we know omega to be equal to c. Rather, we know c to be equal to 2.72 radians per second. So we are able to calculate frequency to be 0.4329014452 Hertz. Knowing the wavelength, knowing the frequency, we are able to calculate the speed of the wave. One equation for speed of a periodic wave is frequency times wavelength, f lambda. V, therefore, is just equal to 0.03772538141 meters per second. So we are able to get the amplitude, 0.00327 meters, direction of the wave propagation towards positive x direction, the amplitude, and rather the wavelength, lambda, is equal to 0.087 meters, and then frequency, 0.433 hertz, and finally the speed of the wave, 0.038 meters per second. Next, we have sample problem number 2. A sine wave of amplitude 3 millimeters has y00 equal to negative 2 millimeters. Determine the phase constant of the wave. So, amplitude of the wave, 3 millimeters. So, Ym is equal to 3.00 millimeters. Y00, y at x is equal to 0, t is equal to 0 is given, negative 2.00 millimeters. And we are being asked to determine the phase constant. The problem tells us that we have a sine wave. The general equation for a sine wave we know to be y is equal to ym sine of kx minus plus omega t plus phi. If we set x to 0 and t rather to 0, you have y00. Y00 is just equal to negative 2 millimeters. So y00 is equal to negative 2 millimeters is equal to ym sine of 0 plus, minus plus 0 plus phi. Ym is amplitude. We know ym to be 3 millimeters. So we have negative 2 millimeters is equal to 3 millimeters sine of phi. Isolating sine phi is just equal to negative 2 over 3. Getting the inverse sine, we have the phase constant. Phi is just equal to negative 0.730 radians. Next, we have sample problem number 3. A sine wave with wavelength of 1.4 meters travels along a string of linear mass density 25 grams per meter. The time for a particular point to move from maximum displacement to zero displacement is 0.135 seconds. So say you have a wave on a string of linear mass density 25 grams per meter. You have a sine wave from maximum displacement. The particle moves towards zero displacement. It takes 0.135 seconds to travel that distance from maximum to zero displacement. If the amplitude of the wave is 5 centimeters, so from maximum displacement to equilibrium position to zero position, this amplitude is 5 centimeters. Determine the speed of the point as it reaches zero displacement. Determine the particle velocity of the particle as it reaches the equilibrium position. What is the tension in the string? So wavelength is given 1.4 meters. Linear mass density, mu is equal to 25 grams per meter or 0.025 kilograms per meter. The amplitude is given 5 centimeters. So ym is 5 centimeters. Convert to meters. The problem tells us that it takes 0.135 seconds to go from maximum position to equilibrium position. One whole wave or one whole vibration is from here to here, back again to the original position. 1, 2, 3, 4. From maximum to equilibrium position, that's just 1/4 of the whole vibration. That means this is just 1/4 of one period. T is equal to 0.135 seconds is quarter wave time. Time for 1/4 of a wave, which means the period is just 4 times the given time. 4 times 0.135 seconds will give you 0.54 seconds. We are asked for two things. We are being asked to determine the speed of the point as it reaches equilibrium position, the zero displacement position, as well as the tension in the string. So V at Y is equal to 0 and F what we are looking for. So we know the period to be 0.54 seconds. This is a sine wave. The position function is just the wave function of the wave. Y is equal to ym sine kx minus plus omega t plus phi, general equation for a sine wave. Getting the velocity function, we simply differentiate y with respect to time. We get minus plus omega ym cosine of kx minus plus omega t plus phi. The maximum value of this equation is simply the amplitude of this equation, which is omega ym. So Vy max is omega ym. We'll be able to get the maximum value of the particle velocity of Vy if we know the angular frequency, since we already know the amplitude ym. Angular frequency is just 2 pi frequency or 2 pi over period. We know the period to be 0.54 seconds. Thus, we are able to know or determine the angular frequency omega. So simply substitute 2 pi over period into omega for our equation for Vy max. Vy max is equal to 2 pi ym over t. Plot in the values. We are able to calculate the maximum value of the particle velocity. 0.58177,641.73 meters per second. Now, Vy max, which we have just determined, is the answer for A, since maximum particle velocity happens at the zero displacement position. Y is equal to 0. This happens because the velocity function uses the cosine function. The velocity function uses the cosine function, whereas the position function uses the sine function. When sine is maximum, cosine is minimum. And when cosine is minimum, maximum rather, when cosine is maximum, sine is minimum. So sine is maximum, cosine is minimum. If cosine is maximum, sine is minimum, and minimum sine will give you minimum y. What is the minimum value for y? Equilibrium position. Y is equal to 0, which means maximum particle velocity happens at y is equal to 0, which is what we are looking for. V at y is equal to 0. Thus, V at y is equal to 0 is just the maximum particle velocity value, 0.582 meters per second. Next, we look for the value of the tension in the string. We have a periodic wave. V is equal to F lambda. F is just the inverse of the period, so V is also equal to lambda over T. We know the period, 0.54 seconds. The wavelength rather is also given, 1.4 meters. Thus, we are able to calculate the speed of the wave, 2.593 meters per second. Now, not only do we have a periodic wave, we also have wave in a string. Thus, the speed of the wave is also equal to square root of F over mu, where F is the tension in the string and mu is the linear mass density of the string. We are looking for the tension, so isolating F is equal to mu V squared. Mu is given, V we have just determined, thus we are able to calculate the value of the tension in the string. F is equal to 0.168 newtons. And that's it for now. That's it for our discussion on examples part 1. We'll continue our discussion on wave motion in the next video. In the next video, we take a look at the concept of superposition of waves.